Hi, good afternoon. This is Mr. Cassidy, and today we're going to be talking about equilateral and isosceles triangles in Chapter 12, Lesson 4. So we've got a few theorems to go over and then some application of those ideas. So the first idea is equilateral triangles. Let me just get my pen out so I can mark on the slide. Great. So here's some vocab you've got. Legs are like the two sides of the isosceles triangle that are equal. Then the base would be the other side. The base angles are on the base line and touching the leg, and the vertex angle would be at the top. An equilateral triangle would be marked like this, and whenever you've got an equilateral triangle, all three angles are 60 degrees. They have to be, because it has to be 180 degrees in total, and all three are the same because these side lengths are the same, the width has to be the same of the angles. So let's dive into this a little bit. So we've got two main theorems. Now we just went over all that vocab, so I'll skip that. But the base angles theorem basically is that if two sides are congruent, basically if the triangle is isosceles. So the base angles theorem is if it's an isosceles triangle, then the two base angles have to be congruent. So then, in this case, B would be congruent with angle C. So then we know those two angles are equal. Then we have the converse, basically the opposite if-then. If two base angles are congruent, then we have an isosceles triangle. Then we have two sides that are congruent. And we'll apply that throughout our lesson today. The problems aren't too bad. Let's get into it. First, this is our brief proof. I won't spend too long here, but this is a proof of that base angles theorem. Basically, we start with triangle ABC, this outer triangle, and what we know is that AC is equal to AB. And so we know that it's an isosceles triangle, so what we want to prove is that angle at corner B is congruent with corner C. So the way they proved it is with the side angle side theorem. First, they created a bisector. They created the angle bisector here of AD, and based on that bisector, we know that these angles are equal, and this side splits it into two congruent triangles. So now we've got a congruent triangle on the top, a congruent triangle on the bottom. Well, what does that mean? Well, that corner C has to be the congruent angle with corner B. And so by first proving that side angle side exists, by making an angle bisector, we end up learning that those corresponding parts of congruent triangles are congruent. That is what Miss Carter abbreviates as CPCTC. Corresponding parts of congruent triangles are congruent. And so angle B is congruent with angle C. Right, carrying on. So you could try this out. This is, I believe, problems 1 and 2 from our journal here. Oh, no, they aren't quite, but it's a little bit of practice. If HG is congruent with HK, so I'm going to go ahead and mark that, what two angles are congruent? Remember, use three-letter naming. For angle K here, we can't just name it with one letter. So I'm going to go ahead and say the answer. You should be able to figure out that angle HGK, that's here, is congruent with HKG. Great. Next, if KHJ is congruent with KGJH, then what do we know? So KHJ, so here I've got this angle, is congruent with KJH. This, what do we know is congruent? Well, we would know that this side, HK, is congruent with KJ. HK, remember to use line segment notation here. HK is congruent with KJ. All right, some corollaries here. Corollary to the base angle theorem. If a triangle is equilateral, then it's equiangular. So if it's equilateral, notice like here we would have sort of an isosceles triangle. These two are equal. So that makes these two angles, A and C, equal. And then we have the third side is equal too. Well, that would mean we could look at the isosceles sort of sideways and say, oh, well, that means this angle is equal. And last, the corollary to that is if the triangle is equiangular, then it's equilateral. So if we start with three equal angles, then it also has to be equilateral. All right. So go ahead and complete the statement. State which theorem you used. I'll let you start. And we're back. So NJ is congruent with NM. NJ, NM. There we go. So to me, that would mean angle J is congruent with angle M. Since there's only one corner there at J and M, I can just use one letter. Okay, if LM is congruent with LN, LM, LM, so let me mark that with 2 now. LM is congruent with LN. Well, I've got to say that those two do not look congruent, but if LM, oh, sorry, LM, that's why. LM, there we go. So it's this corner. Then what is congruent? We would know that corner M, angle M, is congruent with, and here I'd need to use 3-letter naming, at that corner LNM. Okay, next, NKM. If angle NKM, that's this angle here, I'll mark it with 3, is congruent with NMK. These markings are getting a little bit challenging. Well, then I would know that KN is congruent with MN. And last, if I know that LJN is congruent. Okay, so here, I'm going to just leave one marking here. LJN is congruent with LNJ. What do I know is congruent now? Well, there's so much to figure out here. Well, I would know that LN is congruent with LJ. Ton we can figure out from that diagram. All right, moving right on. Use the isosceles and equilateral triangles. So in these problems, we're just going to use those values and those rules in order to figure out things like, for instance, here, I have an equal angular triangle. And so if this side is 4, then I know that y has to be 4. And here I have an isosceles triangle. Well, I'm going to put in y is equal to 4 here. And this side would have to be 4. And notice that this side, NL, has to also be equal to this side, x plus 1, because here it's an isosceles triangle. So I'd do 4 is equal to x plus 1, and I would know that x has to equal 3. All right, there's all that stuff, blah, blah, blah. Moving on. So try it yourself. What do we know about x here? Pause and go. Hopefully you figured it out that fast. X is 31 because it's an equal angular triangle. Next, 2x. What do we know about 2x here? Well, I know these are 12. So I know that all 3 of these corners have to be the same, and they have to add up to 180. So if 6x equals 180, then x would have to be 30. 6x is the sum of these 3 corners, and 3 corners of a triangle have to add up to 180. Okay, moving right on. Last 2 problems for today, and then there's sort of an application problem. Here you have problems 7 and 8. Go ahead and take a stab at them, and then I'll solve them. Okay, let's begin. Well, I know if this is x, and that would mean, and these two are y degrees, then x has to be here, and here, and here. And so here I can see that x actually is equal to y minus 25. Interesting. Okay. Second, I know that y is here, and this is a 90-degree angle. Hmm. Uh-oh, I'm getting stumped here. How do we find? I mean, the value of y minus 25 is x. The value of... Oh, I see. Notice we have an equilateral triangle. Sorry, sometimes it takes me a bit. I preview most of these questions, but I still have to solve them on the fly here. If we have an equilateral triangle in the middle here, or on the right-hand side, I guess, or lower triangle, then that means that this is 60 degrees. So now I can find this missing corner. That's a 90-degree angle, so this has to be 30 degrees. Well, now I can start working backwards and finding y, because y is in this corner, y is in this corner. So 2y plus 30 equals 180. From there, I would subtract the 30 and get 2y is equal to 150. So y is equal to 75. And I already found out that x is equal to y minus 25. So I know that 75 minus 25, that's 50. Okay. X is 50, y is 75. Okay, hopefully number 8's a little bit less challenging than that. Let's get into it. Here I've got, again, a equilateral triangle, so I know that each of these sides are equal. Oops, that's where my pen runs out. Oh, and this is x degrees. So actually, I'm going to start by solving x. X is right here and right here, so that means x plus x is 2x plus 40. And 40 is in this corner, so I'm going to add that up to make 180 and solve for x. Subtracting the 40, I get 140, 2x. So x is 70. And down here, I've got the fact that x minus y equals, because it's equilateral, 2y plus 10. So let me move that up here so I have some room to work. I already know that x is 70, so I'm going to do 70 minus y equals 2y plus 10. And I'm going to just sort of move my numbers around so I get subtract the 10 and I get 60, add the y, I get 3y, divide by the 3, and I get y is equal to 20. There you have it. All right, folks, we found that x was 70 and y was 20. And our final problem. Explain how to prove that QPS is congruent with PQR. PQR and QPS. Well, let's see what we have. PS is congruent with QR here. I'm going to separate those. So first I might separate them a little bit, and then I'd label what we have. PS is congruent with QR. PS is here, and QR is here. Next, QPS is congruent with PQR. QPS is this angle here, and PQR is this angle here. Well, they're sharing side PQ. That's already given to us. That's a reflexive argument. So because of that, I have side, angle, side. Side, angle, side. So now that I know that I have two congruent triangles, both on the outside. So if I want to prove that, I've proved now that both triangles are congruent. Part B, explain why triangle PQT is isosceles. PQT is isosceles, PQT. Interesting. From that, I know that these triangles are flipped around, meaning that Angle 1 is congruent to angle 2 because they're both corners of those triangles. So angle 1 and angle 2 are right here and here. Those have to be congruent because those are the corresponding parts of these two triangles. So now, since I know those are congruent, I can use that isosceles rule, the converse of the base angles theorem, to prove that PT is congruent with QT, which means that PQT is isosceles. All right, well, I hope you're doing well. Be safe, be well, and keep in touch. I'll see you later. Bye.